Hi, I'm Songlong Xing from University of Trento, Italy. In this video, I'm going to introduce our work entitled as SpectralCLIP, Preventing Artifacts in Text-Guided Style Transfer from a Spectral Perspective. Recently, text-guided image style transfer empowered by CLIP, termed as CLIP styler, has become the dominant method in image stylization tasks, as it overcomes the need for a reference image that describes the target style, and can transfer the target style to the input image simply with a textual prompt. However, Clip Styler tends to generate undesirable artifacts. In this work, we identify two types of artifacts, which are textual artifacts and visual artifacts. Textual artifacts are written words that appear on the image. These written words usually come from the textual prompt. For example, when the target style is pop art, the output image using clip contains written words such as pop. The other type of artifacts is visual artifacts, which are irrelevant objects present in the image. For example, when the desired style is pop art, there will be appearance of red lips in the output image. Here, we also show that applying SpectralCLIP proposing our work can remove the artifacts effectively while keeping the desired style. Recently, some researchers proposed to employ spectral analysis in the representations of birds and decompose the linguistic information into multiple granular levels. For example, the low-frequency components of bird representations correspond to long-range semantic levels such as the document level, whereas high-frequency components can correspond to short-range semantic levels such as phrases or words. Empirically, we find that the scales of artifacts present in the image are determined by the styles and correspond to certain frequency bands in the visual representations output by the clip's vision encoder. Therefore, we draw the inspiration of spectral analysis and propose to alleviate the artifact issues inherent in the clip model. SpectralCLIP is a plugin component independent of the downstream tasks. In this work, we use the base version of Vision Transformer as the clip vision encoder in our experiments. Specifically, we take the representation of the final layer corresponding to each patch, along with the class token, and flatten the representations into a sequence of 50 indexes. Then, we apply discrete cosine transform, or DCT, to each dimension, filter out certain frequency components, and transform the representations back to the spatial domain. In this way, we can remove the frequency components that cause the artifacts in the images. Since SpectralCLIP is independent of the downstream tasks, it can be easily plugged into existing methods to address artifacts issues. To simplify our method, we split the frequency components into 5 bands, following the previous work of spectral analysis on bird representations. Empirically, we find that the artifacts are highly related to 3 combinations of the bands, just as shown on the right. For each target style, we use one of the combinations and mask out the corresponding frequency components. In order to select a suitable combination for each style, we use a single content image and choose the combination that leads to the cleanest output image based on visual inspection. Here, we show some of the qualitative results of image stylization using CLIP and SpectralCLIP. As we can see here, using CLIP leads to artifacts spread over the whole image, whereas using SpectralCLIP can prevent artifacts in the output images while keeping the desired styles. We further compare SpectralCLIP to CLIP and forget to spell CLIP, which is a subspace that learns only visual concepts and ignores written ones. As we can see here, CLIP leads to both textual and visual artifacts, and forget to spell subspace of CLIP avoids textual artifacts effectively, but not visual artifacts. In comparison, SpectralCLIP can prevent both types of artifacts effectively. As we can see from the table here, SpectralCLIP reduces the similarity measured by learn-to-spell clip significantly, indicating that it avoids artifacts effectively. Although it also reduces similarity measured by clip, this is because in the training process, the clip similarity is used as the optimization objective. Therefore, this metric is biased for clip styler, where the non-filtered representation is used in the training process. Additionally, we carry out a user survey to investigate the user preference on image stylization using clip, forget to spell clip, and SpectralCLIP in terms of the overall performance, which takes into account the overall visual qualities of stylization and the artifact-free performance. It turns out that over 55% of the users prefer our results in terms of overall performance and over 74% in terms of artifact performance. These results show that SpectralCLIP can produce clean, stylized images and can well present the target style. Since SpectralCLIP is a plugin component independent of downstream tasks, we further extend the proposed SpectralCLIP to image synthesis. Specifically, we replace clip with SpectralCLIP and use it to guide image generation with a VQ GAN. When we use clip, the synthesized images contain written words. In comparison, using SpectralCLIP prevents written words entirely. The results here show that SpectralCLIP can be employed to scenarios where artifacts are undesirable. To sum up, our work analyzes the patterns of artifacts of clips guided stylized images from a spectral perspective. Secondly, this work applies DCT, or discrete cosine transform, to the vision encoder of clip, proposes 3 general filters to alleviate artifacts effectively. Finally, we extend our work to text-guided image synthesis and show that it can prevent written words on the images. Thank you.